Baik, Assalamualaikum warahmatullahi wabarakatuh. Good evening, good afternoon, ladies and gentlemen. So, welcome to workshop of the international guest lecture from Professor Gauss Guido, and to the Honorable Head of Environmental Engineering Study Program, Mr. Fajri Anugroho, to the Honorable Associate Professor Gauss Guido from Teknik University as our main speaker today, and beloved participants of today's event. First of all, let us pray and praise Allah Subhanahu wa Ta'ala. Because of His blessing and mercy, we can come together without any obstacle here, with healthy condition in this international guest lecture of mass balance. Second, let us greet and pray to our beloved Prophet Muhammad, who had brought us to the path of light and left the darkness in this life. Okay, ladies and gentlemen, before we come to the main session, let us start today's session with praying first, so that the event that we will hold on to this day will run well without any obstacle at all. Pray based on individual belief begins. Then, ladies and gentlemen, on this very nice occasion, let me deliver the structure of the event today as follows. For the first event, we'll have opening and greetings and opening by the head of Environmental Engineering Study Program, Mr. Fajri Anugroho, and then we'll have online photo sessions. And then we go to the main event, that is the workshop of plastic waste technology and management in mass balance and analysis of plastic waste pyrolysis. And we'll have a discussion session after that, and then we'll have a closing. So ladies and gentlemen, before we will now invite the head of Environmental Engineering Study Program, Mr. Fajri Anugroho. Time and place is yours.
Okay. Okay, thank you for MC for this time. I would like to say thank you for Honorable Associate Professor Klaus Guido from Teknik University as presenter in our workshop about plastic waste in this afternoon. Also, I would like to say thank you for all participants come to our workshop. I hope that this event make our better understanding about the plastic waste. As we know, in Indonesia and also in other developing countries, many kind of plastic used in daily life for many purposes, such as coffee cups, shopping bags, snack packaging, bottled water, is everywhere, every day. Indonesia generates about 175,000 tons of waste, or about 14%. Yeah, or 24,500 tons a day of plastics. Unfortunately, yeah, currently 81% of waste in Indonesia is unsorted. Yeah, making it difficult to recycle, causing plastic waste to the end in landfill or leak into the ocean instead. As plastic take hundreds of years to degrade, as we know, plastic in landfill and ocean will continue to pollute for several generations. According to World Bank Indonesian Marine Debris Hotspot Rapid Assessment, yeah, we know that about 20% of plastic waste in Indonesia is believed to end up in rivers and coastal water. Looking at this fact, plastic waste is a very serious issue to Indonesian's environment. We have to prevent and manage it better as soon as possible. Our environmental engineering study program in the University of Brawijaya has a responsibility to make a better life environment for the future. And the end of our speech, I would like to say thank you for very much for Professor Guido for giving knowledge about how to handle plastic waste or how to proceed them to the benefit material or product. Okay, thank you very much for all participants come to this workshop and please enjoy this workshop and take benefit. Thank you very much.
Okay, thank you, Mr. Fajri, for the opening speech. Now that the speech has been delivered by Mr. Fajri Anugroho, we would like to have a photo session today to commemorate today's event. So for all the participants, I would like to ask to turn your camera on. So for the participant, please turn on the camera. We will take a photo together and to commemorate today's event. I would like to ask every participant that if there's not any obstacle, please turn on the camera. Once again, I would like to ask the participant to turn on the camera, so we'll take a photo session together. Okay. Okay, I think that's enough. So let's take a photo session together in 3, 2, 1, cheese. Okay, again. 3, 2, 1. Okay, thank you. So let's continue to the next event. So for the next event will be the main event today, that is the workshop of plastic waste technology and management. So today's event will be delivered by Associate Professor Guido Graus and will be moderated by Dr. Evi Kurniati. So I would like to invite Dr. Evi Kurniati for to moderate the sessions, and time and place is yours.
Thank you very much, moderator, for delivering the session to me. Yeah. So, welcome, Guido Sensei, to our study program. Hopefully, we really hope you can come to our study program. But yeah, due to this pandemic, we can only do this, but in the future, we hope you can really come physically in our study program.
Thank you very much.
Yes. Okay, my name is Evi Kurniati. Today I would like to deliver this workshop about the fabulous business. It will be delivered by Guido Sensei, and yeah, here as I can see here, the participant is coming from various backgrounds. Mostly, we also have here our alumni. So yeah, this is a very good session for them to develop their knowledge about the mostly plastic waste management in the real field. Okay. Some of them is also coming from practitioner because yeah, I have joined in a group about waste treatment, mostly in plastic and other waste for energy, waste for circular economy, something like that. So hopefully this session is also useful for them. do the practice in the real life. Okay, without further ado, I would like to give the time to Guido Sensei to deliver uh, your material. Please, time is yours.
Thank you very much. I will just share my screen. And okay, I hope you can all see the screen. Before I start, I just want to tell you what is the plan today. As my as you already mentioned, this is about plastic recycling, or I did experiments in plastic recycling, but today my topic is more, will focus on how to do a mass balance. And since this is called a workshop, I do not want just talk the whole time by myself, but I expect that you also participate a little bit in this. And I provided an Excel or 2 Excel files for you, which contain some gaps, and I hope we will be able to fill these gaps to the end of this session. Yes. So and this this workshop, or the content of this workshop, is related to an experiment that a student and I did maybe about 8 or 9 years ago, and it was about the hydrolysis of polybisphenol A carbonate at 400 degrees C in a fluidized bed reactor. And if you want to read more about this, you can have here the reference, and you can have a look on the data which were published. So the content is that I would like to talk about. I will introduce a little bit about mass balances, because mass balances, and I think that the knowledge that you can get here is not only important for plastic recycling. You can use it for any kind of reaction that you do in a larger equipment, or also a smaller equipment, and you need to know what gets in and what gets out. So I will introduce the equipment we used, then I will tell you how to prepare a mass balance in 7 steps. And I will provide the conclusions that we took out of the experiment. First of all, maybe I should explain a little bit about polycarbonate. Polycarbonate is a major polymer which is used, for example, in computer casings, as you can see this, and especially it is used for optical discs, and also for other applications which require high, very good optical properties. The production is not that high, only 5 million tons per year. This is much lower than that as you have, for example, for polyethylene or polypropylene, where you have 60 or 70 million tons a year. But this is more technical polymer, which is not used that much for packaging. So the reaction that we actually did in the reactor was you can see there. This is polycarbonate hydrolysis. So what we get out there is bisphenol A and carbon dioxide as the main products. Other ways to recycle polycarbonate is mechanical recycling, where the material is only ground and then remelted and used again. And other types of chemical recycling is solvolysis, where actually in the same reaction as we carried out in a heterogeneous phase can be also done in a liquid phase with water, or you can also use different types of other solvents, alcohols, or also ammonia. To the mass balances that we do today, the knowledge that you can get here, you can also use, for example, for biomass conversion, for example, pyrolysis or gasification, even for other types of conversions, transesterification for biodiesel production or fermentation. This knowledge that you gain should be useful. The most important thing when we start a mass balance is it says already that it's a balance. So we have a process. Into this process, we have substances that get in, and we have substances that get out. So we have an input and an output. And under optimal conditions, the input should be equal to the output. This is what we want to reach. So we will measure what we put into the reactor, and we will measure what gets out of the reactor. Therefore, we have to see what actually we have to balance. Input is the equipment, because we cannot expect that after the reaction our equipment stays clean, and therefore we have to measure the equipment before and after the reaction to actually obtain the difference of the material that sticks to our equipment. Then we have input materials. In our case, we have the polymer, the polycarbonate. We use water for the reaction, and we have a catalyst. In our case, this is magnesium oxide, and the catalyst is equal to the bed material in our fluidized bed reactor. Then we have output. So we measure again our equipment, and we have product fractions, which can be solid, liquid, and gases, and we can find them in different parts of our equipment. There are some materials that could be excluded from the mass balance. In our case, we used an inert gas, nitrogen, which would only disturb because it is difficult to balance, and anyway, we do not really need it, and so we will mostly ignore it. So this is the equipment that we used, at least most of that. So what you can see is on the left side, a preheater, which heats up the gas that gets into the reactor. What we cannot see is before the preheater, there should be a steam generator, which provides actually the water in the form of steam, which is then heated up more in the preheater and gets into the reactor. The reactor is filled with magnesium oxide as the fluidizing material. Directly into the fluidized bed, the polycarbonate is transported by feeders. You can see them on the left side, not very clearly because a bar is in the way, but anyway, there at the top of the feeders, there's also a storage vessel, which you cannot see in the moment. And from there, the material gets directly into the reactor, in contact with the catalyst and into contact with the steam gas phase. At the top, the products get out of the reactor. First, and then it gets into the separation unit. First, we have a cyclone. The cyclone separates solid materials that are not gases from the gas flow. These solid materials is mainly abrasion from the catalyst. From there, it gets into a steel cooler where the gaseous materials start to condense. And from there, then we have two, actually in the equipment we used in this special experiment, we had only one glass cooler and an impact precipitator, which helped to remove solid compounds from the gas flow. So actually solid condensable compounds, because the products from the from our reaction are mostly phenols, and these phenols are all solid at room temperature, and we had some problems to separate them from the gas, and therefore we used this impact precipitator. I think I have later a picture about that. And at the end, we have an electrostatic precipitator. This electrostatic precipitator actually removes the condensed materials from the gas stream because voluntarily they are not separated by the coolers. And therefore, most of the materials that we actually got as a product ended up in the electrostatic precipitator. From there, the gas leaves the reactor, and at the end, you cannot see it here, we have a gas meter which counts how much gas is produced. To give you an image of what happens in a fluidized bed, you can see on the right side an image where you can see that we had magnesium oxide in the reactor, and steam was bubbling through this magnesium oxide material and expanding this bed in a way that the behavior is almost like a liquid. And into this bed, we put then the polycarbonate. The polycarbonate gets in contact with the hot catalyst and is immediately melted and covers the surface of the catalyst, where it can then undergo the reaction with the steam. So this are some pictures which we made at a lower temperature to give you an imagination what actually we observed as products. This was at a temperature of 360 degrees C, which we considered then really as impossible. You can see that all the equipment got quite blocked, and the reaction also in the did not work very well in the reactor. On the left side, you can see the impact precipitator, which is something like a nozzle where the gas speeds up and then is led onto a plate where condensed droplets get stuck, and they are then separated into the flask. In the middle, you can see the connection to the glass cooler, and you see that there's a lot of solid material stuck into this tube. This is mainly bisphenol A, which came out of the reactor after the reaction. On the right side, you can see the flask below the cyclone and the steel cooler. In the cyclone, you can see a lot of bad material, magnesium oxide. The reason why it got there was that we had problems with fluidization of the experiment because the reaction in the fluidized bed was too slow, and the polycarbonate got stuck in the reactor, and so we needed to increase the gas flow, which actually caused a lot of the material actually got out of the reactor. So now, if you have questions, please ask. This is a workshop, and so I do not want, so I actually want you to ask questions about the procedure. And when you have questions, please ask immediately and do not wait to the end. We can solve problems of understanding immediately at the spot, I think. Do you have questions until now? If this is okay, then we can go forward to the mass balance. So, step 1 of our mass balance is we have to measure what gets into the reactor and what gets out of the reactor. So, the first step is we measure our equipment before the experiment. This means even though this is quite a big equipment, so this is still, and this is called a benchtop reactor. In spite of this quite large size, we have to measure a lot of this equipment. And we start, for example, with measuring the water container plus the water inside, then the plastic sample that gets into the sample holder, then the bad material, which is magnesium oxide, which goes into the reactor, and then we have to measure the sample holder plus feeders, the cyclone and the cyclone flask, the steel cooler with the flask, the impact precipitator with the flask, the gas coolers, which actually it was only one glass cooler, and the flask below the glass cooler, the electrostatic precipitator plus flask, and the product vessel where we emptied the flask when they were full. So we gathered all the products in the product vessel, and then in the end, the empty flasks were measured. So this procedure was then repeated after the reaction. And what you can see is we got a difference. So what we can see is that the water container, about 1,300 grams of water we used in this experiment. Then the plastic went completely out of the plastic was completely used in this reaction. So, and we recovered most of the bad material. Then we measured also again the equipment, and you can see that quite some materials were stuck in the coolers. They did not get into the flasks and therefore not into the product vessel. So this is the reason why we have to measure everything, because in the product vessel, you can imagine that most of the material there is condensed water, while in the equipment, quite a lot of the material is actually organic. So we have quite some material that we have strictly to consider for the reaction. As I said, it's a mass balance, and therefore the input and the output should be equal. What we see here is this is not completely true. We have about 72 grams of loss. However, one thing we have still to consider, and this is that at this point, we did not include the gases, because the gases we cannot measure by a balance. The gases were determined, or the gas production was determined by a gas meter. The calculation of these data will come later. So this is the analytic way which we used for all the product fractions. So we have solids, we have the bad material, which contains, after the reaction, still some organic material, which was then detected by combustion, and therefore we obtain the content of residue in the bed. We have then different organic fractions. We have organics dissolved in the water, and we have, despite of that, we have an organic phase which is completely solid, because our main products were bisphenol A and phenol, both have a melting point above room temperature. The organic material was extracted with diethyl ether, and then organics and water were then measured by GCFID and GCMS. We had also to use HPLC because we found that bisphenol A was not stable at the GC column, and therefore we had to use another method. And we used MALDI-TOF, but actually not for the mass balance, but for the identification of some compounds. Then solids, where the solid material was removed from the water by filtration, and then it was dissolved. And then and after the solution, we could actually find the inorganic content in our product fractions. And we determined the water content by Karl-Fischer titration. Gases were determined by GCFID and GCTCD. And from that, we could calculate the gas composition and then make a gas mass balance. So now we get to step 2. In the first step was rather the recovery of our product fractions. Now we have to separate the different product fractions from each other. Therefore, we used different procedures. The first thing that we did was we measured the feeders, and we found that some 2.4 gram were still in the feeders, which are obviously polycarbonate that did not enter the reactor. So we will just save that as polycarbonate sample. Then we have to analyze the bad material. The bad material was in the beginning magnesium oxide, but after the reaction, we cannot be that sure about this anymore. So what we did was we took a sample of the bad material, and it was then heated at 800 degrees C for the removal of the organic material. And from that, we got then, we determined the weight loss. And from that, we could say that 412 grams of the bad material was still in the reactor, and 20 gram were organic material that we call residue. So it is not polycarbonate sample anymore because it underwent heat treatment, and it was changed during this process. Then the next thing we did was we had to care about the cyclone fraction. The same procedure as that in the bad material, and we found that actually in the cyclone fraction we have about 24% of residue, which is higher than that in the bad material, but actually only less than 4 grams of residue was obtained there, which is less than that what we have in the bad. After that, we calculated the cooling system. The cooling system, in the cooling system we found some solid material, which we analyzed for their to what fraction they belong, to the bad material, the water, to water or organics. So the organics were, so what we did was we dissolved the material, found that a certain amount of the sample was magnesium oxide, which we measured to be about 2.1 gram. Then by Karl-Fischer, the water content was determined. And in the end, after that, we assume that actually the organic content, which is about 76% in this, or 27 gram, in which we have in the cooling system, has the same composition as the organic compounds that entered the product vessel. So we did not further analyze the organics from the cooling system. It can be made, but I do not think that that the effort actually makes a lot of sense. Then we had the product vessel. The product vessel, we first got the organic phase by filtration, because the organic phase is solid. And by this, we obtain a water phase, which still contains organic compounds. The organic phase was then dissolved and again filtrated, and by this we obtained the amount of magnesium oxide, which was in the product vessel. So these are now mainly the fractions that we have to analyze one by one. Okay, then we come to step 3. This is the analysis of the organic fraction of the solid, which was dissolved. I think it was in DCeta. And we analyzed it after that by GCFID. What you can see here is a typical chromatogram from our products. It contains phenol, tertiary-butylphenol, isopropanylphenol, and bisphenol A as the major compounds. Naphthalene is a standard that we used to determine the weight of the different compounds. And we have quite a big peak which we were not able to identify. Now we have from the hydrolysis of bisphenol A, from the hydrolysis of polycarbonate, we should expect bisphenol A. If bisphenol A is degraded at high temperatures, we can expect phenol and isopropanylphenol as the products. The question is then, where did the tertiary-butylphenol come from? And the answer is, this compound is not really, it is not related to bisphenol A as the main monomer in polycarbonate, but it's actually an additive. Well, it's actually included into the polymerization process. It's an molecular weight modifier. As you know, when you want to produce polymers, polyesters, and actually polycarbonate is a polyester, then your monomers need two functional groups, as bisphenol A has. It has two hydroxyl groups, which act as the functional groups for the polymerization process. And only such compounds can actually form polymers. However, to modify the molecular weight, it is frequently used. It is often done that you add a compound which only has as one functional group, and these monomers or these compounds actually come then to will stay at the end of the chain. And when by adding a certain amount of these compounds, you can actually control how many monomer units will form the chain, or you can control the polymerization degree. And for this purpose, butyrylphenol is used. So now to our next step. This is step step 3, the analysis of the organic fraction by GCFID. When you open your Excel file, you will find this under the slide of condensed. And you will see that there are some gaps in your file, which are filled in now on the PDF file. And now we want to see what is required to make to determine the content in the organic fraction by GCFID. So for this purpose, we did actually 6 runs, which we from which we formed an average. We put as a standard, as an internal standard, naphthalene into the sample, and you can see the amount of sample in the table below the main table. So actually this table has now not a number, but the it's called material. And what you can see there is we had total organic fraction, and from that we took an organic sample of 4.5 gram and added 0.2 grams of naphthalene. What I actually forgot to say is the red numbers are numbers that we measured by ourselves, and the black numbers are actually calculated values. So when you find a red number, this is what we measured. And yet now you can see that we measured this sample 6 times, and you can see that we divided then the peak areas of each compound by the peak area of the standard naphthalene. And this helped us actually to normalize the different runs, because when you inject into a GC, you cannot really be sure that you always get the same amount into the GC, and this might have an impact on your results. And therefore we normalized at this point actually the area, so that in the end we obtained an average area. You can see we also calculated the standard deviation. And what you can also see from there is that the standard deviation of bisphenol A was quite high, and therefore we decided that not to rely on GCFID for the determination of bisphenol A. In the next step, we need a response factor, because when you measure compounds with GCFID, different compounds have different responses in the detector. Actually, the GCFID is very comfortable because there are possibilities to calculate these response factors. Therefore, I provided another file which is called mass balance RF value. I hope you have this file, and this file allows you to calculate the response factors for compounds in the for the FID. So you can see here as an example the calculation for bisphenol A, and yes, actually, I would like you to calculate the response factors at this point. Please try to calculate if you are able to obtain the response factors that are required in the red fields in the table where with the compounds and the response factors. Are you able to do that? Please try to calculate these values. You should I should maybe explain this a little bit more. What you have to do for this is you have to add the number of C atoms. Let's take as an example, bisphenol A. So bisphenol A has 15 C atoms. Then we have 16 H atoms and 2 oxygen atoms. Then you have to calculate the number of carbon atoms which do not have any heterobonding, so no contact to oxygen, but at least one hydrogen atom. You will find that these are 10. So you have 4 in each phenylalanine group, and then 6 together with the methyl groups. And then you need to calculate the number of carbon atoms with an heterobonding and an H atom. This would be, for example, an aliphatic hydroxyl group or an ether group. But in our example, bisphenol A, there is none, so this is 0. Then you can go to the right column, and there you find several functional groups, and there you have now to select the functional groups that are present in your molecules. And in our case, this is in the case of bisphenol A, we have 2 phenolic alkyl groups, so we add the number of 2, and we will obtain a response factor. Actually, we obtain 2 different response factors. Method 2 is more accurate than method 1, and we can then calculate different response factors for different compounds. Why do we have 2 methods? Because we cannot use, there are cases where we're not able to use method 2. For example, if there are functional groups that are not included in method 2. Or, well, mainly this method 2 can mainly be used for hydrocarbons and oxygen-containing compounds. If you have something else, then you have to use method 1 to get a response factor. So I think we are a little bit, we should a little bit hurry. So I will leave it to you to make the calculation later. You will, at the end, you will get also the original mass balance file so that you can see actually how the calculation works. And you can try to find the right result by yourself. Okay, so did you understand the response factors? Everything clear? If there are no questions, we can go back to this file. And so what we did now was we calculated the response factors, and by this we can obtain the mass in the sample by comparing the peak sizes with the mass of the naphthalene standard. From there, we calculate then the mass in the sample, and from there we can also conclude the mass in the solid fraction, which is now, without bisphenol A, almost 18 grams. So bisphenol A we obtain by a different method, by HPLC. This is then table 3b. And we found that actually the amount in the sample was 2.5 grams, which makes 78 grams in the total solid fraction. Then the step 3c, was the water determination by Carl Fischer titration. And in this case, we found that our organic fraction has still a water content of 19%, which is quite high, but also reasonable because all the compounds that we have are phenols, and therefore the water uptake is quite high. I forgot something else, and this is we have also, next to our main products, phenol, phenol, butylphenol, and isopropanol phenol. We have also we found also other compounds by GCFID. We identified them in a real mass balance, or when I would do this, I would not exclude them. But since I want to make it short in this workshop, I put them all together into others. But when you have others, then other compounds, then how to define actually the response factor? And the response factor is defined then as an average of the unknown compounds. You can make it in a different way, but we kept it simple and said that our unknown compounds should have similar properties, and therefore also the response factor should be similar to the average of all compounds that we found. And so after that, let's go further to step 3D. This is the composition of the solid fraction. So what we found here was that that we have an organic fraction of almost 96, organic content of 96 gram, water content of 26 gram, and we have also not detected not detected compounds of 16 gram. This is the difference between the total solid organic fraction minus the organic fraction and organic content and the water content. So everything that we were not able to determine at this spot, we did not detect. So, and from there we can then make a mass balance of this organic fraction, which contains phenol, tertiary butylphenol, isopropanol phenol, bisphenol A, other compounds that we were able to detect, and compounds that we were not able to detect. This you can see in our step 3E. Let me have a look. In step 3E, I was a little bit confused, but in the table 3E, these are the compounds, or the composition of the compounds from the cooling system. So I was just confused that the amount was quite low, but these are the compounds, the composition of the organic material from the cooling system, which should have the same composition as the compounds in the in the product vessel. So